what we just did. All right, so we are talking about our method of undetermined coefficients. We're looking at the example, second derivative of y minus 3 times y prime plus 2y equals 3e raised to negative x minus 10 cosine of 3x. We already found that the homogeneous solution is equal to c1 times e to the x plus c2 times e to the 2x, and we use the characteristic equation to find that. We then made a guess, and your guys' guess was totally right, where you look specifically at our individual pieces of our non-homogeneous part and match the exact same guess like you would normal. This is something you can extrapolate out anytime you have things added together for each one of the pieces that you have. Right here, just go ahead and write down what you would normally have for those two terms. And in this case, because we had a trig function, that gave us two terms in our guess. And again, I am not going to go ahead and have a solve for A, B, and C right now, just because for this particular problem, it takes a little bit of work, but I will go ahead and post the full solution for this particular example so you can see start to finish what you would see in terms of your homogeneous part, which we did, in terms of getting the actual answers for A, B, and C, which we didn't do, and then step 3, let me go ahead and write down step 3 here. So there is a missing bit for us to solve for what is A, what is B, that's the part I'm skipping, what is C. Step 3 is your actual answer would be your homogeneous part plus your particular solution, and that H looked terrible. And there you would just drop the two answers in you got from step 1 and step 2. Okay. Questions make sense? Kind of okay at this point. All right, so I do have an example prepped up at a little bit more towards the end of today where we'll do everything. We'll set up step 1 with the homogeneous bits. We'll get the full particular solution, solve out for all the unknowns, and put it all together. But for right now, I just wanted to get us what would the format of the particular solution look like. All right, so let's look at the other example. The other example here is the second derivative of y minus 2y prime minus 3y. And this guy now equals 5 times t squared times sine of 4t. And no typo in this differential equation, luckily. All right, so again, if you wanted to, you could skip out on dealing with step 1. Step 1 does deal with our associated homogeneous differential equation. So find the homogeneous solution. But let's go ahead and do it. So first thing you would do is convert to your associated homogeneous differential equation. Don't overthink it. The term that only has independent variables or only has constants in it, convert it to 0. And the question I just saw come up, it was C equals question mark. So in that box, actually, I think I can go back to it just a second. In this box right here, that was not trying to be a 2. I'm sorry, the dot didn't come in. It was trying to be a question mark. I actually, just a second, let me look over to the side. I've got this question worked out. It actually, if you're interested, turns out to be they turn out to be 1/2 72 over 13 and 9 over 13, or what those constants of A, B, and C actually turn into. And I'll go ahead and post that as well. So they all turn out to actually be fractions. Yeah, sorry about that. That is totally just that the dot didn't show up. All right, so going back to the example we're currently working on, we go and we grab our associated homogeneous guy. So our non-homogeneous part just turns into 0. Then we grab our characteristic equation, which looks really, really similar to what we had before. And if we were being really, really proper, we would actually over here to the side say, hey, our second derivative turns into r squared, our first derivative turns into r, and our regular old function turns into 1. So then we factor this thing, And because I rearranged where our 2's and our 3's were, it will factor slightly different than before. Did anybody happen to get the 2 factors? And while you guys are thinking about that, I'm going to prep up with the roots equal. Oh, and you gave me roots instead of factors. Okay, so this one here is going to be should be r minus 3 and r plus 1. Do a quick double check to make sure I wrote them in the right order. So I see you guys wrote it in several things. I'll match what I've got with the factors here, which would be 3 and negative 1. It doesn't matter which one of these guys you call root 1 and root 2, because at the end of the day, we're going to add things together. And when you add stuff, it doesn't matter if you add thing 1 first or thing 2 first. So then associated with the first root and the second root, we have our 2 solutions. Anybody got what those 2 solutions are going to be? So our 2 solutions will be e to the 3x. I lie. Just a second. Why did I say I lie? What should be in that exponent? Why would I say the x was the issue? Ooh, 3x is what I tried to write. Yeah, so watch out. This is the thing that happens to everybody, and in fact, it happened to me over there on the side right here too. That scribble is supposed to be a t. Why would we know that our independent variable here is a t? Don't overthink it. Okay, yeah. It is actually given, and it is given right here in that non-homogeneous part. Because we have t's, that means our independent variable better be a t. So when we actually write out these 2 different elementary solutions, or just the solutions for your homogeneous differential equation, they would have t's as opposed to x's. Watch out, it gets everybody. You notice it just got me because I naturally went to x's. So then if we wanted to be very precise and we write down what our homogeneous solution would equal, this would be some constant c1 times e to the 3t plus some constant c2 times e to the negative t. And I'll go ahead and put step 3 here at the end. Notice I'm totally jumping ahead here. Your actual solution will be that homogeneous guy plus whatever you get from your particular solution, and you just drop it into the slots once you have them. Here we just found homogeneous guy, so you could actually drop that first part into this first position right now. But because I didn't leave myself enough space there at the bottom, I'm not going to worry about dropping it into that format for your actual solution in step 3 yet. Now, the actual question here only asks us to figure out the format of our particular solution. So the actual question here is only talking about our step 2, the only thing we haven't done yet. So anybody have a guess on what our particular solution's format should look like? Don't overthink it. This one's a little trickier than the last one. Actually, let me do a little bit of a lead-in for you. So what we've got in our almost. It's a little bit more complicated than that guess. Here's the lead-in. Notice in our non-homogeneous part, we have 2 big pieces. They're not added together, they're multiplied together, and yes, that last answer would work. You can actually make it slightly more simplified than that. So I'm going to walk us into that answer. So here, the factor of the 5t squared would turn into a second-degree polynomial. So something times t squared plus something times t plus some constant. And your sine of 4t is going to turn into a format dealing with trig functions. So that's our something, and I'm going to match the same way that you wrote it, something times cosine of 4t plus something times sine of 4t. Yes, these can get crazy nasty, crazy fast. Okay? Now, Notice where each of those two pieces and parts, the 5t squared and the sine of 4t, came from originally. That's where you're going to drop in these general formats of your function. So what this tells us is that your guess for the particular solution is exactly the same as a times t squared plus b times t plus some constant c multiplied by both of these two guys. So this would be multiplied by cosine of 4t. Because I ran out of space, I'm going to go ahead and factor this, or really distribute it. I have the same a times t squared plus bt plus c. And realistically, I shouldn't have done it quite like that. I really should have done it with a different letter, so let me back up. You can say maybe something like dt squared plus et plus f times sine. Now, that is not quite the same as the guess that's in our chat. The guess in our chat is 100% correct. Any guesses why I would say this is also a way to write that same thing? Did you guys notice what I did? And again, either one of the two is perfectly fine to do. So what I did is I simply took and multiplied the polynomial part, so this at squared plus bt plus c, on both the sine factor as well as, I said it backwards, on both the cosine as well as the sine term. And notice here I went ahead and changed these coefficients because the coefficient on the sine, if you originally called it whatever you called it, would be multiplied through on all three of the polynomial terms. Same exact deal down here, whatever coefficient was originally on the sine would be multiplied through on all three of the polynomial terms. So while I have minimal space to do it up here, if you're writing this down in terms of notes, you might put a middle step that's that closed, only two-factored form that we've got up on the chat. Actually, I might be able to fit it in here. So let's try. Or, here's our polynomial. Please fit cosine. Oh, I think it's going to fit plus sine. And depending on you, it's your preference which of those two you like better. And some people prefer to go ahead and multiply out each term of the polynomial too. And at that point, you'll get a cosine term, a t times cosine term, a t squared times cosine term, and similarly for sine. Okay. Notice, we are not going to be solving for those unknowns. This one actually takes a lot of work to solve for the unknowns. And it's not that it's super, super difficult. It's just that it takes a long time because there's so many unknowns. And when you start taking the derivatives, notice you've got derivatives and product rules. They just explode as you go through them. Again, I do actually have this all worked out, and I did actually was able to fit it all on one page, but it's very, very tiny writing. So I'll go ahead and post that for you if you want to see the full worked solution for this particular example, but I'm not going to do it live. Questions kind of make sense in terms of how we handled the guess in these two last examples, where it wasn't just a straightforward polynomial, exponential, or trig function. But notice we did the same thing. We grabbed the forms that we would normally grab and then put them locationally where they should have been, or where they were, where their, what's a good word for it, where their little function that they correspond to lived in the non-homogeneous part of the differential equation. Questions before we move on to something very related but a little bit theory, a little bit more theory. Your book, if you read in this section, and I believe this is at the tail end. Yeah, this is at the tail end of section 4.4. Your book, your author actually writes out this ginormic formula with tons of cases of when to do when. I'm not going to lie, I find it even confusing when I try to read it. So feel free, if you want to see that, go for it. He's got a formula that tells you exactly what to do and when to do it. But the rule of thumb really is use the same format matching that we've done in the past and just insert those general forms for your functions where your original functions that were given, how they're put together in your non-homogeneous part. That's the trick. All right, so next thing, since I'm seeing no questions from you guys, is something called the Superposition Principle. I don't care if you remember the name Superposition Principle, okay, as long as you can read through a question and figure out what's going on. So here's what the Superposition Principle says. It basically talks about what we've just been doing. It says, suppose you've got y1, and we're just going to call this guy a particular solution of some non-homogeneous differential equation. Normally, you would call this y with a subscript p, but I'm going to have a second differential equation, which is why the 1 is there instead. Okay? So you've got some constant coefficient second-order differential equation, because it was easy to write out, and went ahead and said you've got the non-homogeneous part, and again, a subscript here of 1, because we're going to have a second differential equation. So then for the second differential equation, which has the same coefficients as the first differential equation, notice these guys match right here. Okay. The only thing that's different is your non-homogeneous part changes. So now your particular solution for that second non-homogeneous differential equation is potentially different. Okay. Then this principle of superposition, or the superposition principle, goes as follows. It says, all right, well, suppose you take the exact same first part of your differential equation as before, but now you take your two non-homogeneous parts and you multiply it by some constant, like a 2 or a 3 or whatever constant you want. Then it turns out if you take the original particular solutions of your original two differential equations, if you multiply and add them together in the same orientation that you did with the non-homogeneous bits of your original two differential equations, you will then find a particular solution of the new differential equation. This right here is exactly what we were doing on the first example that we had on the last slide, where we had our two things that we knew how to deal with normally, and we just added them together. Okay? Same idea. So let's see how this would actually work in practice. Okay. So notice this just says that you're going to grab your particular solution based off the individual terms, which is, again, what we just did in the previous example. So next slide is going to be the actual example. So here's all the information, and then we're going to walk it out down below. So suppose you have a differential equation of second derivative of y minus first derivative of y plus y all equals sine of t, and you're told that cosine is a particular solution of that guy. Are there more solutions? Definitely, but cosine is a solution. Okay? And you're given a second differential equation, which is the first part with the y's is identical to the last differential equation, so still second derivative of y minus first derivative of y plus regular old y, but now your end is different, so equals e to the 2t instead. So notice our independent variable in both of these cases are t, and we're told now if you have e raised to the 2t but multiplied by 1/3, that's a solution of the new differential equation. So we're going to use those pieces of information to answer the following questions. So the first question is, could we figure out what a particular solution is for this related differential equation, which is second derivative of y minus y prime plus y equals 5 times t? Any guesses what we could do here for a particular solution? Could we use method of undetermined coefficients? Of course. If we use method of undetermined coefficients, it would look like this. And then we'd have to solve for the a and the b. But I am going to claim that we can do it a whole lot faster. And instead, the answer is yes to what you just guessed. Notice here, if we compare this ending to our very, very first guy, the first parts match exactly. The last part, the non-homogeneous part, is you just multiplied the sine times 5. So that means your guess for your particular solution would be 5 times whatever the particular solution is of this first guy. So I'm going to write y1, which of course when you sub it in is going to be 5 times cosine. Don't forget the t as I almost made it an x. Okay. Makes sense? Feeling okay-ish? Questions so far? Since I can't see you, feel free to vote with little checks or X's if you're feeling okay or not okay. Okay, I see a couple of you are feeling okay. I don't see any X's yet. Excellent. You guys are awake. Awesome. Okay, so what happens if we do something slightly more complicated? So suppose we have this next example. Huh? Ooh. So let me back up. So I actually crossed off the whole thing, not just the sine, but also the cosine. I crossed it off because while that method will totally work, we did a different method. So up here, this is undetermined coefficients method, and you'd solve for your A and your B. Down here, I used superposition. I'm just trying to show you guys a shortcut. It's literally all I got for you here. You can't actually do this method of superposition this fast unless somebody already tells you what your solutions are. One of the ways that people use this is if they have a complicated situation like, let me throw in this next one. They have a more complicated situation like this. What they will sometimes do, and let me do this over, how about over here? What they'll sometimes do is break this into 2 pieces, and they'll say, hey, let me look at my differential equation when it equals sine, solve that one, make my life easier, and then look at my differential equation when it equals this, maybe just e to the 2t bit. I'll be able to create my own y1, y2 solution, and then put it all together. So that's often how this is used in practice, as opposed to being given these 2 solutions off the top. So yes, we've got a guess. So in this particular case, key things to look for are your coefficients. So for your coefficients right here, we've got the 1 and we've got that -3. That tells you in terms of formatting, your particular solution for this new differential equation should be 1 times, look where the sign came from, so 1 times y1 minus 3 times y2. And then you just drop them in, which should be exactly what I think I saw the guess to be. That would be cosine t minus, well, 3 times 1/3, the 3 and the 1/3 will cancel, so that will be a minus e to the 2t. Okay. I went ahead and put that middle step in there to go ahead and show you where the different things are coming from. You guys feeling okay? Comfortable so far? That's literally all superposition is. It's nothing any more complicated than that, so do not overthink this. Okay. So let's look at the last example, and you guys see if you can figure out what the particular solution would be here. I see 1 guess that came in, 2 guesses that have come in, and then for the same function. You guys think that they are correct? All right, so let's check it out. So here, I'll go ahead and put in a middle step for us. Key things to look at are your coefficients out front, and make sure you watch what your coefficients were on your original non-homogeneous parts. Other thing you want to make sure to do is you always want to make sure that your part with all the dependent variables is exactly the same as your given differential equations up here, in our case in the red background. If not, this method doesn't work. So you have to have the terms with the dependent variables have to be matching. So we'll have 4 times y1 plus 18 times y2 So we drop that in, and that would be the easy part would be your cosine. Make sure I get the right t. And then the plus 18. So 18 times 1/3, there's where you get your 6. So it looks like you guys are totally spot on. Okay. Questions make sense? Feeling kind of okay about superposition? Okay. If you guys do have questions, let me know, and we can come back to this slide. Otherwise, we'll go. I've got one last example for us that it looks like we'll be able to start today, but we might not be able to finish today. If we don't finish today, we'll finish it up Thursday after we deal with all the practice test 2 stuff. So, just as a last follow-up, you guys do have a Canvas quiz that talks about superposition. I believe it's due Thursday night, and it would be asking you to see if you can do the same sort of thing. Okay. All right. So, next example, and this is the last example that is prepped up in this section, and it is not asking you for any one single part of what's the particular solution or what's the format of the particular solution. This guy puts it all together and says, solve for the solution. Okay, so this is the whole thing, everything together. So, first step that you want to do is you want to go ahead and deal with your homogeneous solution. That same thing that we did on several of our previous questions that we actually didn't have to do. I always recommend people, especially when you're first doing this, to go ahead and write out your homogeneous differential equation. Do you have to? No. If you can just see it and go to your characteristic equation, you can. But to cut down on errors, especially when you're first doing this for the first time, it's helpful to add in that extra step. Then we can convert to our characteristic equation. And since we've done this a couple of times in the past, I'll just go ahead and convert here. So we've got r squared plus 5r plus 6. And I'll go ahead and write the conversion to the side while you guys see if you can grab what the factors are. And that'll give us time to grab your answers. So the conversion over to the side was second derivative converts into r squared, first derivative converted into r, and regular old y converted into 1. And did anybody happen to get the factors of r squared plus 5r plus 6? Okay, yep. So you guys sent me both roots and factors. So in this particular case, we're going to have r plus 2 and r plus 3, and it doesn't matter which order you write it in. Remember, with 2 pluses, the plus in front of the 5 and the 6, you'll get both pluses there, which means your roots are going to turn out to be both minuses, so minus 2 and minus 3. So this guy is going to turn into a solution of e to the negative 2. Quick check, is our independent variable tx or something else? X's, so we'll put in the x, which means our homogeneous solution is going to be c1 times e to the negative 2x plus c2 e to the negative 3x. We are definitely not going to finish this example today. All right, so let us at least get to the guess for our particular solution. So anybody have a guess for what format our particular solution would look like? Remember, you want to look at your non-homogeneous part. Ooh, almost. You don't need the E at the end. Yep, that one works. Looking good for those of you coming in. It is standard to go ahead and use capital letters here when you're writing them out. So we'll have ax squared plus bx plus c plus d times e to the x. So that'll be our guess. Now, quick check. Do any of those terms match our homogeneous solutions up here? If the answer is no, this guess is good. If the answer is yes, we have to adjust the guess. You guys are both correct that answered in so far, as well as those of you coming in. None of those terms that we just wrote down in our guess match the 2 original functions up there, which means we're totally going to be able to solve for a, b, c, and d. We'll take the derivative 2 times. We'll plug it into our differential equation that we have up here, and we'll be able to solve for A, B, C, and D. So we've only got a little bit of work left to finish that. Wow, the algebra intensive work, but a little bit of work left to finish it, and then we'll get to our final answer. Once we actually figure out what A, B, and C, and D are, we'll add it to our homogeneous solution right here, and that would be our general solution to the non-homogeneous guy. But we'll finish that up next time, and we'll also remember at the beginning of next time have a practice test for us.